We're going to hear a lot today about, have already, and we'll hear some more about Yuda's scientific contributions. But one of the things that isn't often appreciated is, a great scientist like Yuda, in addition to their individual scientific contributions, is the contributions they make towards mentoring other young people who go on in the field and make contributions of their own, and then mentor other students, et cetera, et cetera. And it feels a little bit funny to think of myself as a young person, but at one point I actually was. We've heard from Rena and Hector, who were both students of Yuda. We heard from Dana Now, who had no direct connection to Yuda, but received a strong boost. And I want to tell you another story along the same lines. And Yuda was not my PhD advisor. I did my PhD at Carnegie Mellon. And I want to take you back to 1984, which was 26 years ago. It's a long time ago. I was an assistant professor at Columbia University in New York City. And the official title of Columbia University is Columbia University in the City of New York, in case people are confused it with other places. I'm not sure why. So I was interested in the following problem. I was interested in heuristic search, and I certainly was aware of Yuda because Yuda was, the giant in heuristic search. And the problem I was interested in was the following. And the observation was that normally in heuristic search, we're looking at a combinatorial space. So we have a problem like Rubik's Cube or the 15 puzzle or the 8 puzzle. And what we do is we search it. We start with some initial node, and then it has children by applying a set of operators. And then those children have children by applying operators, et cetera. And what happens is it eventually blows up exponentially. The number of nodes grows exponentially with the depth to which we search. And we normally think of the problem as fundamentally a problem of time. If it's going to take exponential time to solve these problems, we're not going to be able to solve very big problems. And in that day, people would use the 8 puzzle as a classic example, and people could find optimal solutions to the 8 puzzle because it's really very small. There's only about 100,000, a little bit less than 200,000 states, so it's not a problem. The observation was that yes, time is a problem at some point, but memory was actually a bigger problem. So the standard algorithms of the day, for example, the simplest one is breadth first search. And I forgive you for those of you who are search people and have heard me rant about this for 25 years now. For those of you not in the field, the basic idea is behind a breadth first search is we start with our root node, our initial state, and then we generate all the children of that state, the successors, by applying one set of operators. And then we generate the children of those, and then the children of those. And what we do is we store them all in memory. Okay? And so if we start with an initial state, we generate its children. We say we close that initial state. So the states that we've already expanded and generated all their children are considered closed. They go on a list that we call closed. The children which have been generated but not yet expanded, we haven't generated their children yet, are what we call open nodes, and we put them on an open list. And the observation is if you take a very simple algorithm like breadth first search and you run it on your computer, and again, we're back in 1984, what happens is you run out of memory. And you run out of memory very quickly. You run out of memory in a matter of minutes or less. And you say, well, okay, that was in those days. Now we have much bigger memories, right? There we had a few K of storage. Now we have gigabytes of storage, right? So let's fast forward to the present, okay? You take your laptop, or I take my machine, and I've got, say, 2 gigabytes of storage. That seems like an enormous amount. Maybe the memory problem has gone away. But unfortunately, over that time, computers have gotten faster as well. Okay? So if I take my machine now with a 2 gigahertz processor, and let's say I can generate on a simple problem on the order of 10 million states in the course of a second, and let's pretend it takes 4 bytes to store a state, a 32-bit word. And if I've got 2 gigabytes of memory, my memory is going to last me all of 50 seconds. Okay? So after 50 seconds of running my algorithm, I'm stuck because I've filled up my entire memory. And what's interesting about this phenomena is over that span of time, the problem hasn't really gotten much better. It hasn't gotten a whole lot worse either. But essentially, memories have gotten bigger, computers gotten faster. We still have the same problem. So I was trying to figure out, so how do we solve this problem? What do we do about it? And it turns out, the answer turns out to be relatively simple, deceptively simple. And many of you know the answer, of course. And the answer is, instead of doing a breadth first search, what we'd like to do instead is utilize a depth first search. And what a depth first search does, it starts with one node, it generates its left child, and then it generates its left child, and it keeps going down the path until it decides to backtrack at some point. And then when you backtrack, you abandon what you've done and you go down a different path. Now, the nice thing about a depth first search is normally the way you implement a depth first search is you implement it recursively. And the only memory you keep, you don't keep all the nodes you generate. The only storage you have is you have the path of the current nodes from the initial state to the current state where you happen to be at. It's normally simply stored in the recursion stack of your machine, but the key thing is it's only linear in the depth of search. And if you've got an algorithm whose space complexity is only linear in the depth of search, you don't have a space problem at all. What you have, of course, is you may have a time problem. So this was well known as well, and this seemed like a simple solution, but unfortunately depth-first search has a couple of problems, okay? The first problem is even if you have a finite problem, like the 15 puzzle, the tree, even if the graph is finite, there's a finite number of states, the tree itself is actually infinite, okay? And so what will happen if you simply implement a depth-first search is you'll go down the left branch, and you'll go down the left branch forever. You'll never even find a solution, and what you'll do is simply repeat the same set of operators as you go down that left branch, okay? Another problem, of course, even if your tree happened to be finite, was that the first solution you found may be quite deep, and there may be a much shallower solution elsewhere which you haven't gotten to yet. So the solution quality, so you don't have a complete algorithm, and you don't have optimal solutions. So the solution, in fact, it's borrowed from work that was done in two-player games, was an idea called iterative deepening. And the idea is do a depth-first search to level 1, okay? And if you find the solution, great. If not, do a depth-first search to level 2. If you find the solution, great. Otherwise, start over each time and do a depth-first search to one level deeper. So what does this give you? Okay, all of our searches are depth-first, so the amount of memory is now linear. Memory is not a problem. It ends up being complete because you're evaluating the tree one level at a time. So you're guaranteed to eventually find a solution. And furthermore, okay, the first solution you find is going to be an optimal solution. So what I did was I wrote a paper about this. I submitted it to AAA. I think the title was called "The Complexity of Brute Force Search," and it was mostly kind of reminding people that using this trick, what you can do is you could essentially completely get rid of the memory problem. There's a little bit of tiny overhead in doing the previous iterations, but in practice it really doesn't matter on a tree because almost all the nodes are at the bottom, and for reasons I won't go into right now, it turns out it's actually faster than doing a breadth-first search. So I wrote this paper up, and I thought it was very simple, and I was rather pleased with it, and I sent it to AAA I-84, and they rejected it, okay? And that was a little tough on me. I've gotten a thicker skin in those days. I've had a lot more. The advantage is I've had a lot more papers rejected between now and then than I had at the time. And the reviewer said this is trivial. Okay, and to some extent they were. So I came out to drown my sorrows, and I decided what I needed was I needed a trip to Southern California, enjoy the good weather. So I came out, and Yuda in fact invited me to visit. And so we were sitting in his office, and we were talking about this idea. And what Yuda suggested was basically the way to apply the same idea to heuristic search, to 8-star, okay? And in fact, heuristic search algorithms like A-star had exactly the same problem, okay, which is they ran out of memory in a matter of minutes, okay? And so you could solve the 8 puzzle, but you couldn't even solve the 15 puzzle. And everyone, Ira and other people, always touted the 15 puzzle and said you can use A-star to solve it, but you really couldn't because you'd run out of memory too fast. So Yuda had this suggestion, and we were sitting in his office, and we talked about it, and it seemed like a great idea. I went off and did the implementation. I went off to write the paper, and I invited Yuda to be a co-author on the paper as would be appropriate. And what Yuda said was, no, you should just be the author. And I said, but look, one of the key ideas here is really here. He says, look, I've got lots of papers. I don't need another paper. I have tenure, et cetera. You're new in your career. This paper will matter to you, okay? And what I regret now is I didn't insist that he actually be a co-author on the paper. And so the paper on IDA Star, which was published, there was a version at ICHI in '85, which is actually here in LA, and then there was a version in the iJournal, unfortunately only has my name on it. Okay? If you read the acknowledgement, there's, I hope, an appropriate acknowledgement to Yuda. But that's the kind of guy he is. He's just so generous, and he's, and I think he recognized, probably better than I did, that this was a useful notion. But what he said was, no, why don't you leave it on your own? And I think part of what was going on in his mind, I can't read his mind, was that he was very well known in this area. I was completely unknown in this area. And his concern was that people, in looking at the paper would in fact draw the appropriate conclusion, which was, that he deserved at least as much credit for this as I did. So that's the story I really wanted to tell. It's a story of generosity, and for that I want to thank you. And that's an example of, I wasn't his student, I wasn't even his colleague, I was a Columbia at the time, okay? And yet he gave me this gift, and it turns out that paper has been cited over 1,100 times. I checked yesterday. So when you're counting up Yuda's citation count, you really need to add 1,100. This notion of worrying about space then became kind of a recurring theme, and there's there's a subtext in AI, in heuristic search in AI, and a number of algorithms which were developed. Dana developed an algorithm along this line of dealing with this issue of how do you deal with space. Stuart developed an algorithm along these lines. I've then subsequently gone on to develop a few other algorithms that are really focused on this issue of how do you deal with the space complexity. Given the time, I think I won't bore you with the technical details of any of that, but I just want to remind people that people are contributing in a lot of ways, and Yuta is a classic example. They make their own contributions through their own scientific work. They also end up, the other part I forgot to mention is kind of why I'm here, okay? So I was at Columbia, okay, and I was, Columbia is a great place, and I enjoyed living in New York City. I lived in Manhattan. That was kind of a fun place to be for a couple years, but I didn't really want to be there full time. And what I really wanted to do is I really wanted to be in a place like UCLA, which was, this part of the country was much more attractive to me for various reasons. And so then about around that same time, UCLA was recruiting in AI, and so I saw this ad, and I was excited, and I applied and came here. And I imagine, again, I don't know this for sure, but having sat on the other side, and many of you are involved in faculty recruiting, and what you probably appreciate is, what I appreciate now is I'm really glad I got the job at UCLA in 1985, because looking at recruiting we do now, there's no way I could get a job at a place like UCLA anymore. What we expect and require of our students is just unbelievable, okay? The other thing that goes on, of course, is when someone gets hired at a place, there's almost always a case, there was a champion. There was a member of the faculty who was well regarded and well respected, okay, who championed that individual and said, look, this person's going to be good, this person's going to be great, we really ought to hire them, okay? And I'm guessing, and he's too modest to even tell me, and I wouldn't even ask him, that Yuta probably had to work extremely hard to champion my case, because certainly on my merits I didn't deserve to get the position in the first place. And for that I'll also thank him as well. So thank you, Yuta, for your advice, for your friendship, for your collegiality, and for all of your mentoring of myself and in fact many of the people in this room. So that's all I'd like to say. Thank you.